Hello, Scylla Summit. Today we're gonna talk about transactions. But first, a couple of words about myself. My name is Denis Rysov. So at Red Panda, I designed Red Panda transactions, and before I joined the company, I was at Microsoft testing consistency of Cosmos DB. As a kind of a side thing, I invented Caspaxes, and when I don't stare at the screens. I love surfing in the cold waters of the Pacific Northwest. And today we're going to talk about transactions in Red Panda. But first of all, what is a Red Panda? As you already understand, Red Panda is the name of the company, but also it's the name of the product. What this product is about. Redpanda is a modern streaming platform supporting Kafka protocol. Unlike Kafka, it isn't JVM based, it's written in C++ and it's native. It uses thread per core model, and just like Scylla, it's based on the C star framework, which, by the way, I really like it. Makes so easy to write synchronous code. Thank you, folks, for creating it. Uh, okay, that's Red Panda, but it only gives information if you're already familiar with Kafka. So let's look at the Red Panda from the storage perspective. Red Panda is a specialized distributed replicated transactional storage, which optimized for append-only writes, sequential reads, persistent cursors, and primitives for consumer cooperation. Well, let's describe what it is, but how do people use it? There are multiple use cases for Redpanda. The major ones are to use Redpanda for data transfer. For example, customers may use Scylla, they may connect it with tools like Debezium to Redpanda and then use Redpanda to shift large amounts of data between an LTP database and an ALAP database, such as ClickHouse, for example, to do the analytics. Another use case for using Redpanda is to have Redpanda as a backbone for the event-driven architecture. We may think of a lot of microservices connected with via Redpanda. So this is it. And now the interesting part, transactions. We probably all know what transactions are. It's basically a mechanism to update multiple objects at once with all or nothing semantics. For the databases, the objects are usually rows, and for Redpanda, when we talk about updating multiple objects, it's topics. So with transactions, customers may write to multiple topics at once. And another use for transactions in Redpanda is consume, transform, produce loop. Remember I mentioned about the persistent cursors? It's called consumer groups. And what customer wants is to read data from a cursor, do some transformation, and then write this data to the output topic. And they want to do this operation instantly. So we don't want to process the same piece of information twice, and we don't want to see duplicates in the output topic. Usually when people talk about transactions, they talk about the banking example, so moving money between different accounts, and it's kind of easy to see importance of this problem. So we don't want to lose money, so we want all or nothing semantic for this. Let's see how to map the banking example to Redpanda. So we want to talk about the banking example, and we may have this architecture for our banking service: a list of accounts grouped together and mapped to microservices, and each microservice is backed by Scylla and Redpanda. Scylla holds the current balance of the account, and Redpanda acts as a ledger, just like blockchain, and just like Bitcoin. Each instance of Redpanda contains a list of all transactions touching this particular account. It's if you might think that it's kind of contradicts the microservice architecture because we have different microservices backed by the same storage, Scylla and Redpanda, but actually it's fine here because we may map each microservice to its own table and topic, so nothing is violated in terms of microservice architecture. Now let's look at the operations that it's possible to perform in this banking example. So when the user wants to check its balance or transfer money between its own accounts, we don't need to touch Redpanda. All of the operations happens between the REST interface, a microservice, and ScyllaDB. But when user wants to perform cross accounts operation, we need to involve Redpanda. So how it happens? Each microservice, it has its own ledger, and it's constantly pulling events from this ledger, updates the balance, and saves snapshot to Scylla. When a user wants to transfer money between accounts, it's contact its own microservice. Then this microservice checks that the user has enough money on the account, and then it executes Redpanda transactions to put this logical transaction to multiple ledgers. Remember, we have each microservice has its own ledger, so we need to insert in, if we transfer money between two accounts, we need to insert into two ledgers, and we want this operation to be atomically. So this explains us how to build transactions on top of Redpanda, so how to use it in the banking example. But just because we may build banking examples on top of Redpanda, it doesn't mean that we should. So the next question is why to use Redpanda at all for the transactional operations? And the answer is latency. Imagine two data centers, one in Seattle and another in New York. Seattle data centers is responsible for operations of the users on the West Coast, and the New York data center is responsible for operations of the people from the East Coast. And the problem with the databases is for each operation, they require coordination between both data centers. It happens because of the isolations level. Usually when people use a database, they pick one of the two isolations level, either serializability, and serializability means that all of the transactions are ordered. It means that we can't get away from the coordination. Another option that the people may choose is the snapshot isolation. With snapshot isolation, it's possible to update multiple records concurrently at the same time, but it requires that all of the reads observe the monotonically increasing view of the database. So again, it's an order, and we require coordination. With streaming, it's not true. With streaming, usually, for example, Kafka and Redpanda implements non-monotonic snapshot isolation. And this isolation level, it's just a person who is tiring of being in the control. Do you want out-of-order updates? Okay, just go for it. You want non-monotonic reads? Yeah, you're allowed to do this. The only restriction is to avoid conflicting records. So if people want to execute transactions in the Seattle data center, obviously these operations, they don't conflict with the updates in the New York data center, and it's all may happen concurrently. So we don't need the need for coordination when there is no cross data center transactions. And because of this, streaming may be way faster than the databases. But because we use technology that allows us to be fast, it doesn't mean that we actually achieve this performance. So I've asked on Twitter to just to see people's opinion, what's the expected performance of a replicated distributed database when we're talking about the banking example with transferring money between two accounts. And we see that the majority answers that it's 6,000 transactions per second. And you know what? This is the data for Red Panda. We at somewhere 60 concurrent clients, we achieved this this value. So when we talk about performance, we can compare it with the expectation, what we did, but another thing that we may do is compare it with the existing system. So let's look at the Kafka. So this is data for Kafka. We can see that its throughput is 6 times lower than Red Panda. Of course, if I were you, I wouldn't trust this data because I'm biased and I probably may just mess up with the configuration. And my goal is convince you and convince myself that this data is actually valid. So what I've compared the baseline between Kafka and Red Panda, and then I measured the ratio between the baseline and the transactions. If this ratio is the same for Red Panda and Kafka, okay, this difference is possible to explain by choose of wrong parameters. But if this ratio is different, it will tell us about the differences in the replication protocol. So this is a baseline. We can see that Red Panda is roughly 3 times has throughput 3 times more than Kafka, but for transactions it was 6 times. So it hints us that Red Panda does something different in the transaction department. Let's find out. This is an example of banking transactions in Kafka and in Red Panda. Let's see what is happening when we try to execute this transaction. Begin transaction is a client-only method call, but send already sends the RPC to the server. And send consists of 2 parts. First is adding a topic to a transaction, and second part is sending data to a topic. So this is how we add a topic to a transaction. Client call a register call. If we're happy, this call contains the data for all of the partitions that are being executed. The coordinator saves to disk and replicates this data, and then it's answers to a client. Then client start to execute send request. It send data to a partition. If a client doesn't wait for result of the send operation, it may send data to a different partition too. Then the partition write to disk and replicate it, and then it acknowledges the request. Now the final part is the commit transaction. Client sends a commit transaction to a transactional coordinator. Coordinator writes it to disk, replicates it, and immediately acknowledges the request. Then in the background, it's contact all of the partitions, writes the transactional marker. The mark is being written to disk and replicated, and then it's acknowledged, and then it's marked the current transaction as finalized. So this is a Red Panda. This is a Kafka protocol. Let's see what we can. Let's see on the Red Panda optimizations. So first of all, we allow send to be eventually consistent. It may lead to inconsistencies, but we have it covered. When it's a commit phase, we check that all previously replicated data are up-replicated. So we check that everything is... so we eliminate this possible inconsistent state. Also, we use parallel commits optimization, and we use RAM over disk in the cases when it's possible. Let's see at the flow. So this is a add topic to a transaction. Client sent an RPC to a coordinator. Then coordinator contact all of the partitions in these transactions and ask for its term. Term is something like a version of the current leader, and later we use this information to validate that all of the eventually replicated sends are actually fully replicated. We keep this information in the RAM instead of the disk, and we immediately acknowledge to the client. During the send operation, we don't replicate data, we just write it to disk and immediately answer to the client, and then we replicate this data in the background, so not in the hot path. And the last part, the commit operation. So client calls the commit RPC, then the coordinator immediately start writing and replicating. It's preparing status, and also it contacts all the partitions participating in the transactions to set a barrier. Basically, it's ask if you're the same leader I had talked before, please validate that all of the ongoing send operations are fully replicated. Then once it's get confirmation from the partitions and from the writing these disk operations, we acknowledge the commit to the client. This parallel writing, it's called parallel commits optimization, first introduced by CockroachDB. After we acknowledge the data, we write the prepared state and replicate it, and then we contact the partitions again and ask them to write the transactional marker, and then we keep this. Then we mark this transaction as committed and keep this information in memory. If it is being wiped by the restart, we just retry the commit RPC and it's idempotent, so there's no big deal and nothing can go wrong in this case. So this is a Redpanda optimizations which lead us to this throughput. That's it. Let's stay in touch. I've posted my contacts, but also we have a community Slack at the Redpanda company, and also we have open positions. So if you like to work on the complex distributed stuff, please apply. Thank you.